Namaste and welcome to yet another lecture on linear algebra through geometry. In the last few classes we have looked at vector spaces, vector subspaces, then bases, dimension, and we also looked at the fundamental subspaces associated with a given matrix, let us say A m by n, and we found that the matrix A is going to, if it is going to be an m by n matrix, it is going to transform an n component vector to an m component vector, and in that process we were looking for the set of n component vectors which would get mapped to the 0 vector, the m component 0 vector, and the collection of all those vectors in the Rn which got transformed to the 0 vector in Rm. That collection we called it as the null space of the matrix A, and then we looked at the set of linear combinations of the columns, basically the set of vectors which can be written as the linear combinations of the columns of the matrix A, and that we defined as the column space of the matrix, and that column space of the matrix A was a subspace of the Rm vector space, and the null space of A was a subspace of Rn. And we figured out that associated with A transpose also we had two of these subspaces corresponding to the null space of A transpose, which is a subspace of Rm, and the column space of A transpose, which was actually the row space of A, and that was a subspace of Rm. And when after we established those four fundamental subspaces associated with the matrix, we said that if you have a vector space, you can always look for a subspace in the vector space under the usual operations that the vector space has, like basically the vector addition and scalar multiplication. In addition, if we have this operation, let us say inner product or the dot product, we could also find out a subspace which contains the set of vectors which basically contained all those vectors which are orthogonal to a given subspace of the original vector space, let us say V, and we called that set of vectors which were orthogonal to a subspace of a vector space, we called that a subspace as as the orthogonal complement of the subspace. And in fact we figured out, we took a lot of examples where we figured out a simple example like, okay, in 2 dimension if you take if R2 was the vector space and you had the subspace of R2 which was basically the line passing through the origin and through the vector 1 0, that means entire x1 axis, we said that the orthogonal complement of this guy is basically the set of vectors along the line passing through the origin and the vector 0 1, that means y axis or x2 axis was basically the orthogonal complement of x1 axis. So that is what we saw, and we all know that every set is a subset of itself, and therefore we said that if you take the subspace of the vector space, let us say if the vector space is R2, you look at R2 itself to be the subspace of R2, but then we found something very interesting, and we found that the orthogonal complement of R2 was just the set containing the 0 vector alone. And we also looked at examples where in which we had a line passing through the origin in, let us say, in 3 dimension, and we figured out that the orthogonal complement of this particular subspace was actually another plane passing through the origin. And when we had plane passing through the origin in R3 to be the vector subspace of R3, we figured out that a line passing through the origin and perpendicular to the plane is basically the orthogonal complement of this, and we also established the fact that the dimension of a subspace of a vector space, say W, plus the dimension of the orthogonal complement of W, let us say W orthogonal complement of W perpendicular, was equal to the dimension of the vector space to which they belong to, right. That is exactly what we looked at. So we are going to dwell a bit deeper into this right now, and in the process we are going to establish the relationship between the 4 fundamental subspaces that we have. We are going to look at the orientation of you have two subspaces in Rm and Rn. So what we are going to do is we are going to look at the geometry of these two subspaces of Rm and Rn, like how are they oriented, and that is going to give us some interesting results. So that is what we are going to look at right now. So let us get on. So let us look at the orthogonal complement subspace. So we have the orthogonal complement subspace. So how did we define this? Orthogonal complement subspace. So what I will do is let us start with this. Let V be a vector space. I'll just take let V be equal to Rn. The vector space that I want to look at is basically Rn, and let's say let W be a subspace of Rn, subspace of Rn, let's say of dimension k. Now what do we mean by subspace of dimension k? For example, if you look at V to be R3, this could be a 2-dimensional subspace of R3. So W could just be a plane passing through the origin, it is a 2-dimensional subspace of R3. So we are going to look at in similar terms, we are going to look at V to be Rn and W to be a subspace of dimension k. So by W perpendicular what we mean is this. So the orthogonal complement W perpendicular is basically the set of all those V's in Rn, the set of all those vectors in Rn such that V dot W is equal to 0 for every V in W, so for every W, the W vector in the subspace W, right. So what are we going to do? We are going to look at V to be a vector in Rn and W to be the set of vectors in the subspace W. If we are able to find out such vectors V such that V dot W is equal to 0, that means the dot product is 0, then you have already found a collection of vectors. We in fact proved that this was a non-empty set closed under vector addition and scalar multiplication in the last lecture, and that is going to be your orthogonal complement subspace, right. The most important stuff, some of the properties of this orthogonal complement ideas is basically this, some of the consequences of all these things. So we are going to look at the first one. The first one is let V be equal to Rn, that is the n-dimensional, the vector space is the n-dimensional vector space, and let W be a subspace of Rn, a subspace of Rn. Then we know that W perpendicular is the orthogonal complement, W perpendicular is also a subspace of Rn, is also a subspace of Rn. Now the most important result is that we say W intersection W perpendicular is just the 0 vector, right. W intersection W perpendicular is 0 vector. So how do we prove this? Just a small quick proof, it is a very interesting proof. So we are going to look at that proof. Okay, let V be a vector in W intersection W perpendicular, right. This is the common element to both W and W perpendicular. That means V is an element of W and V is an element of W perpendicular also, which means I can say because W perpendicular is the orthogonal complement of W and W is the orthogonal complement of W perpendicular, we say that we take any vector from W, the dot product of this vector with any vector in W perpendicular must be 0, and what we see here is since V is an element of both W and W perpendicular, I am going to say V dot V is 0, V dot V is 0. And when will V dot V be 0? V dot V will be 0 only when V is the 0 vector, is this right? It is 0, V dot V is 0 That is, what are we looking for? We are looking for that vector which is orthogonal to itself. This implies V vector is just the 0 vector, and therefore what we say is W intersection W perpendicular is just the 0 vector. That is the trivial subspace that we have. I think we have also established this previously, where we looked at intersection of two subspaces. We said that okay, at least will contain the 0 element, and definitely we are going to say, look at this, okay, being 0 element, then you say that okay, it is another subspace, right. Okay. Now let us look at something more. So we already established the fact that the dimension of W plus dimension of W perpendicular is going to be the dimension of V, the vector space to which these two belong to, right. So let us look at this. So how do we do this? So let us look at this. If again let us take V to be the vector space which is Rn, and W a subspace of Rn, Rn. Now what I am going to do is, I am going to write the basis B for V, the vector space V. In fact, I am going to write an orthonormal basis for V. So let us write an orthonormal basis for V. We have already seen what it is to say orthonormal vectors and stuff. So I am going to look at an orthonormal basis. So let B be an orthonormal basis for V. Orthonormal basis for V. Now V is Rn. We already know that the number of elements in the basis corresponds to the dimension of the vector space, and since V is Rn, we must, the basis for V must therefore contain n linearly independent vectors. Here we are looking at orthonormal vectors, so we need to get n orthonormal vectors there. Therefore the basis B, let us assume that the basis B is going to have vectors which are like say u1, u2, etc. uk, comma uk plus 1, comma etc. un. So what does this mean? We will say ui dot uj is equal to 0 if I is not equal to j, is equal to 1 if I is equal to j. This captures our orthonormality, right. Okay, so now what I am going to do is, out of this I am going to look at this W. I am going to say that this is basically a k dimensional subspace of Rn. W is a k dimensional subspace of Rn. Therefore what I am going to do is, I am going to say let u1 etc. to uk be the basis, the orthonormal basis for the vector space W. This is what we are going to have, right. Now what we are going to say is, we are going to say that then the vectors uk plus 1 plus comma etc. un is a basis for W perpendicular. Okay. Now what I am going to do is, I am going to look at this. Let S be the span of, we already know the definition of span. Span is nothing but the set of all possible linear combinations of a given set of vectors. So let S be the span of these vectors, let us say uk plus 1 etc. un, right. Let that be the span of this. Now what we see is, we note that uk plus 1 etc. un is linearly independent and is a basis for W perpendicular. what we want to establish is, we want to establish that the span S and the W perpendicular are essentially the same. So, to establish span S and W perpendicular to be the same, we look at we show two things. We show that S is a subset of W perpendicular and W perpendicular is a subset of S, and therefore that implies S is equal to W perpendicular. This is what we are going to establish. So, that will be the line of proof that we are going to look at. So, first of all, let us look at whether S is going to be, in order to establish S is a subset of W perpendicular, let us look at this. To prove S is a subset of W perpendicular, we can take that any vector x, any vector let us say x is of the form let us say x is equal to dk plus 1 vk plus 1. I am going to look at the basis vectors plus etc plus dn vn for some scalars dk plus 1 etc dn. And what we say is any vector is x of the form dk plus 1 vk plus 1 plus dn vn is orthogonal to every vector W in the subspace W, right. Any vector x of the form, that means x is basically we are saying it is in the orthogonal complement. We know that this vector x is going to be orthogonal to every vector W in the W. So, what we do is, and we know that this vector W can be written as let us say C1 V1 plus etc plus CK Vk for some scalars C1 CK etc. which implies x dot W is equal to 0 implies x dk plus 1 vk plus 1 plus etc plus dn vn dot product with c1 v1 plus etc ck vk is equal to 0, because we already know that this v1 v2 vk plus 1 to vn, this forms the orthonormal basis for Rn, and therefore the dot product of this will be 0, v1 with vk plus 1, v1 with vk plus 2, everything will be 0, and therefore we say that x dot vk is 0. So what we are going to say is, we are going to say that also vk plus 1 etc vn, these are themselves orthonormal, I mean orthogonal, and they are of unit length is orthonormal, and orthogonal to every vector, in the other set of bases for W, every vector in v1 etc vk. Hence we say that x vector is basically an element of W perpendicular, and x vector is basically a linear combination of these vectors, therefore x also belongs to the span of the set of vectors vk plus 1 to vn, which means we are going to say the span S is basically a subset of W perpendicular. Now what we want to do is, we want to prove the other way around, we want to prove that W perpendicular is is a subset of the span. So, to show that W perpendicular is a subset of the span. Okay. Now, what we do is we must show that any vector in W perpendicular, that any vector is also in the span of, is also in the span S. What is this S? S is basically the span of those vectors Vk plus 1 to Vn, right. That is the span. S is basically the span of that vector. So, what are we going to say? We are going to say X is in the vector X is in W perpendicular. So, what we let X be a vector in W perpendicular. So, we have, since V1, V2, Vn is orthonormal basis for is orthonormal basis for Rn, I can write X to be equal to X dot V1. This is basically the Fourier basis expansion which we already saw before, plus X dot Vk into Vk, plus we are going to have X dot Vk plus 1 into Vk plus 1 plus etc. plus X dot Vn into Vn. Now, since X is in the orthogonal complement of the subspace W and V1, V2, Vk forms the basis for W, all these guys will get knocked off, they will become 0, right. So, what we have? We are going to say X is, this implies X is equal to X dot Vk plus 1 in the direction of Vk plus 1 plus etc. plus X dot Vn in the direction of Vn. That means we have established that X is a linear combination of these Vk plus 1 to Vn vectors, which means X is therefore in the span of, in the span S of these vectors Vk plus 1 etc. Vn, which means W complement or W orthogonal complement, what are we going to say? It is basically a subset of S. Now, in the previous part we had S to be a subset of W complement, now we have W complement to be a subset of S, which implies W complement is equal to S, right. So, we have established that the span of the set of these vectors is equal to the W complement itself, and therefore, what is it that we started with? We said that if you have a basis for a vector space X subspace, vector subspace W of a vector space V, what you do is you can extend that basis of W to the basis for Rn or the vector space V by taking the basis vectors from the orthogonal complement. That is exactly what this means. So, what you do, given a subspace V W of a vector space V, let us say W is a k dimensional subspace, let us say V is equal to say Rn, we have, since we know what is the subspace W, we know the basis for orthonormal basis, or we know the basis for W will contain k vectors. The remaining n minus k vectors that we want to get, in order to get a basis for Rn, the n minus k vectors can actually come from, or will actually come from the orthonormal, the orthogonal complement of W. That is what this means, right. Okay. So, let us go ahead. We have already established this properties, quickly let us do that. We have the second thing, which is basically dimension of W plus dimension of W perpendicular is equal to dimension of V, that is exactly what we saw here, dimension of the vector space V. We just saw it now, we had dimension of W, we had k linearly independent vectors or k orthonormal vectors here, V was basically Rn, and therefore the dimension of W perpendicular is n minus k, where the n minus k elements will be there in the basis for the W complement, that is the W orthogonal complement, right. Okay. We just established that. Now quickly let us look at one more thing. Let us take up this 3. This is very important one. We are going to give another interpretation of the orthonormal basis expansion as something else. Let us look at that. So let W be a subspace of Rn, and U1 etc. UK is an orthonormal basis for W. So for every vector, for any vector, let us say V in Rn, I am going to look at a vector, any vector in Rn. I am going to define something. We define the orthogonal projection, of V onto W as projection of V onto W. This is the vector V onto W is given by V dot U1 in the direction of U1 plus V dot U2 in the direction of U2 plus etc. V dot UK, and this is precisely what we saw in the other case as we called this as the Fourier basis expansion. We did that before, right. Okay. This is how we define the orthogonal projection. The fourth and again yet another interesting thing is, let W be a subspace of Rn, let W be a subspace of Rn. So what we are going to say is every vector V in Rn, we will say, can be expressed uniquely, as, let us say, V is equal to V W plus V W perpendicular, where V W is basically an element of W and V W perpendicular is basically an element of W perpendicular. We already know that V can be expressed as a linear combination of the basis vectors. Assume that you have orthonormal basis vectors. You can write this as V is equal to V dot, let us say, U1 into U1 plus V dot U2 into U2 plus etc. V dot UK into UK plus V dot UK plus 1 into UK plus 1 etc. V dot UN into UN. So we can very clearly see that one is basically a projection of V onto the orthogonal onto the vector space W, subspace W, and the components Vk plus 1 to Vn, that is going to be a projection along the W perpendicular case. And in order to prove that the expression is unique, you can actually take two different expressions for V and establish that. So I will just leave that as an exercise. So we can try out. So we can prove that, okay, proof that the let me call this as star. Prove that star equal to V is equal to VW plus VW perpendicular is unique for VU VW in W and VW perpendicular in W perpendicular. I will just leave that as an exercise, it is easy to do. So, we will try that out, okay. You could probably do that. And in fact, what is very interesting is we will see this, that is the most important stuff again. We know that V is equal to, let us say, VW plus VW perpendicular. Therefore, I want to look at the squared length of this vector V, which is nothing but VW plus VW perpendicular dot VW plus VW perpendicular, which is nothing but VW the whole square plus VW perpendicular plus VW perpendicular the whole square. Yet again you will see this Pythagoras theorem coming into play. Now, where do we go from here? Our goal was to establish the relation between the two subspaces that were there associated with the matrix on the Rn side and the two subspaces that were there on the Rm side. We want to look at the orientation of this. So, what we will do is we will just quickly look at the orientation of the 4 fundamental subspaces. Fundamental subspaces of A m by n. We want to look at that. So, let us again write, we have on the Rn side we have null space of A and range of A transpose or the column space of A transpose. On the Rm side we have null space of A transpose and range of A. So, the question is, what is the relation between these two and what is the relation between these two guys? This is what we need to look at, right. So, that is quickly we are going to do. I am going to establish for one side and you can easily prove the other side. So, what you do is let us look at this. So, consider Rn, so let X be an element of null space of A and let A be an element of Rm by n. So, let X be the element of null space of A. That means what we know? We know that this implies Ax is equal to the 0 vector, which is I will say 0 m. Basically, it is the 0 vector on the it is an m component 0 vector. Now, so what we have is for every vector x in null space of A, what can we say about Ax? Ax is equal to 0 m, that is the m component 0 vector. Now, since Ax is basically the m component 0 vector, now what we are going to say is we are going to say this implies Ax is orthogonal to every vector in Rm. Can we say that? Ax is orthogonal to every vector, let us say u in Rm. Why? For x in null space of A. If x were to be in null space of A, then Ax is 0, and because Ax is 0, you take any vector on the Rm side, the dot product of the vector that you have taken on the Rm side with the 0 vector is going to be 0. Therefore, whenever I consider x to be in the null space of A, Ax is going to be orthogonal to the y vector that or the u vector that we have in Rm, which is basically look at any m component vector u, right. Now, what does this mean? This implies Ax dot u is equal to 0, right. This is nothing but Ax dot u is equal to 0. So, I will write this as Ax the whole transpose dot u is equal to 0 for we will always use this for x in null space of A, that has to be remembered. So, we have x in null space of A and this u is going to be elsewhere, I mean it is going to be in I or Rm. So, what is it that we have? We have, so I have x transpose dot A transpose u is equal to 0. Can I do this? X transpose into A transpose u is equal to 0. Why? Because this I can write this as x transpose A transpose u, which I will write this as is equal to 0. I will group it this way. So, x transpose into A transpose u is equal to 0, which implies x dot A transpose u is equal to 0, right, where x is in the null space of A and u is basically in Rm. Now, what is A transpose u? A transpose u we have said for every u in Rn. So, A transpose u is going to put me back into the column space of A transpose, right, and it is going to be, this is going to be an element of range of A transpose or the column space of A transpose. So, what do we see? X is going to be an element of null space of A. We say that every element x in the null space of A is now orthogonal to every element in the range of A transpose, which means we have established that null space is equal to the orthogonal complement of range of A transpose, and range of A transpose is therefore the orthogonal complement of null space of A. So, what do we say in the Rn side? So, in the Rn side we have null space of A is orthogonal complement of range of A transpose, and range of A transpose is orthogonal complement of null space of A. Similarly, we can establish the other one on the Rm side. We can establish that null space of A transpose is basically the column space of A's orthogonal complement, and column space of A is basically the null space of A's orthogonal complement. So, what we have seen, you had 4 subspaces associated, fundamental subspaces associated with the matrix, and 2 of them were on the Rn side and 2 of them were on the Rm side. And it is interesting to note that the 2 subspaces on the Rn side were actually orthogonal complements of each other, and the 2 subspaces on the Rm side are also orthogonal complements of each other. In fact, if you happen to look at the cover page of Gilbert Stang's Professor Gilbert Stang's title book, I mean the cover page of the Professor Gilbert Stang's book on linear algebra, Introduction to Linear Algebra, you will see that he would have done something like this. He would have taken this Rn and Rm, he would have drawn something like this, where we have this so he would have very clearly marked that this is the null space of A, this is the range of A transpose, this is range of A, and this is null space of A transpose, clearly seeing that these are orthogonal subspaces. Yes, and I am going to have X in Rn. It is interesting to see that we have already proved that when you have 2 orthogonal subspaces, any vector in that vector space can be uniquely expressed as a combination of one component along the subspace W and another component along the W perpendicular. So, any vector x can now be expressed as, the vector x can be written as x as a component along the null space of A plus x as a component along the range of A transpose. Similarly, any vector B here can be expressed as a linear combination, I mean as a component along the range of A transpose plus a component along the null space of A transpose. Yeah, okay. Having done all these things, now where do we head to? Remember, from the time we were looking at these subspaces and stuff, we were talking about we were looking at Ax equal to B, and we said that Ax equal to B, if consistent, That means if consistent, we are going to find out the values, the scalars x, such that B can be written as a linear combination of the columns of A. That means you have solution to exist. We have completely neglected the part where Ax equal to B is not consistent. That means B is not in the column space of A. So what do we do? And that is what we are going to see in the next module in terms of least square solutions. So what did we cover in this module? We had looked at the four fundamental subspaces in this module, namely the subspaces of A m by n. We said we have null space of A associated with the dimension which is called the nullity. This was the nullity, and we had the range of A. We call this the associated with the range of A is the rank of A, that is the dimension. So this is the dimension, let me put this here. Then we had null space of A transpose, which was basically associated with this nullity of A transpose. Then we have range of A transpose, or the column space of A transpose, or the row space of A, whose dimension is also the rank. And we combined all these things, we put all these things definitions together, where we said the rank is equal to the number of free variables plus number of pivot variables, or number of pivot variables plus number of free variables in row reduced echelon form. We equated the number of pivot variables to be the rank and number of free variables to be the nullity. So we looked at that, and then we looked at orthogonal complement subspaces, and we also established the relation between null space of A and range of A transpose. We also established the link between range of A and null space of A transpose. These two are orthogonal complements of each other, and these two guys were orthogonal complements of each other. We looked at all that, and in the next module we will start looking at least square solutions, where the vector B is not going to be in the column space of A. Thank you.